attack model, which is the CPA security, right? So recall that CPA security was supposed to be the case where the parties can get access to, well, they can request encryptions of messages that they like. And the way this is formalized is as follows. So now the challenger is going to generate a random key K, okay, as before. And the adversary A is, given the security parameters input and is given Oracle access to the encryption function with the key built in. Okay, so the adversary cannot actually see the key. The only thing the adversary can do is feed in some message and receive the corresponding ciphertext. And given this ability, so given as input the security parameter and Oracle access to this encryption function, without explicitly knowing the key, that's important. So that's what Oracle access means. So the only thing you can do is you can ask for evaluations of the Oracle or the function on whichever inputs you wish to specify. Okay. So given this, the Oracle is supposed to produce messages M0, M1 and send it to the challenger. The challenger is, as before, going to sample a random bit and then encrypt one of the bth ciphertext using he'll just encrypt the bth ciphertext, the bth message to obtain the ciphertext C, and then give it back to the adversary. And we call C the challenge ciphertext, right? So this is the one that we want decrypted. And the adversary is now going to continue to have access to this encryption oracle and is supposed to make a guess B prime for which message was encrypted by the challenger. Okay, and the experiment succeeds, or the verifier accepts, the challenger accepts. These are just different words, okay, to the same thing. The challenger accepts if B prime equals B and loses otherwise, or rejects otherwise. Okay, and the security is the same, that a scheme satisfies the CPA security, right, or is CPA secure if the game above can only be won with probability at most half plus negligible. Okay, and there are some immediate observations here, right? So first of all, it might look like this definition is impossible to achieve, right? Because an adversary that outputs M0 and M1 and then receives this encryption, right? So a very simple attack is to just imagine that the adversary runs this oracle encrypt on the messages M0, M1 and learns C0, C1, okay? And then whenever the challenger gives C, the adversary can simply compare whether the challenge ciphertext C matches C0 or C1, right? And so you'll know whether B was 0, 1. But the crucial thing here is that we're kind of implicitly assuming, which was also mentioned in class by someone, was that this encryption is deterministic, right? So we make that assumption to make this argument work. And so basically what this shows is that if you want to have security against chosen plain text, then they cannot be deterministic. By they, I mean the encryption scheme, at least, cannot be deterministic. It has to be probabilistic. Okay, so every time you run enc, it will produce a potentially different ciphertext. Okay, or let's just say with very large probability, it will produce a different ciphertext. Okay, good. How do you construct such a scheme? So maybe one thing that I already mentioned, did I mention it? Okay, yeah, so before we look at the constructions, we look at one final model of security, which is this last one, which is the CCA model of security. So the CCA model of security says the following, that the challenger is, as before, going to sample the key K by running gen 1 to the n, and then the adversary A is given 1 to the n, the security parameters input, is given Oracle access to the encrypt and decrypt functionalities, and it is supposed to output messages M0, M1 of equal length, because if let's not get there, because the ciphertext could be correlated to the length of the message, and then it's trivial to distinguish and so on. So, but okay, let's not get there. Okay, so you get the adversary gets access to the security parameter, oracle access to encrypt, and the decryption oracle. Okay, so that is the key part. Okay, and now the adversary is free to run however many invocations of enc and dec at once to produce these messages M0, M1, which are sent to the challenger. The challenger is going to choose a B uniformly at random, and then encrypt a ciphertext using this, the Bth message. He would encrypt the Bth message to obtain the challenge ciphertext C and send it back to the adversary. And the adversary continues to get access to the encryption oracle and the decryption oracle, with the only constraint being that the decryption oracle cannot be queried on the challenge ciphertext itself. Okay, that's it. And then eventually A is going to output the bit B prime. Okay, and the output of the experiment is going to be 1 if B prime matches B, right? Because that's what the adversary was trying to do, trying to guess the value of B prime. Okay. So we did have a small discussion about this in class, right? Whether, how do you physically prevent the adversary from decrypting if they have access to the decryption oracle. But like we said, this is just an abstraction for capturing the most powerful adversary. Of course, if the adversary in general could decrypt everything, they could decrypt the message we want, we're saying. But if the only limitation is that they cannot decrypt the message that has been challenged, and otherwise they are given essentially access to everything we can possibly conceive of, short of decrypting the same message, then even then the scheme stays secure, right? And that's a very powerful notion. Okay, and then we say that a scheme is CCA secure if the above game cannot be won probability half plus negligible. Okay. So these are the other two notions of security I wanted to add in addition to this indistinguishability that we looked at in class.